Welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to talk about moments of inertia with areas. The definition for the moment of inertia, which is also called the second moment of mass, and it's also called the rotational inertia, is the tendency of an object to resist change. So before we get into the formulas, I just want to give you an example I think you can relate to. If we took a regular object, like a rectangular plank, and if we were to calculate what the moment of inertia is when the rectangular object is placed this way, or if it's placed this way, we would find that they each had very different moments of inertia. When the plank is placed this way, the moment of inertia is much less than when it's placed this way. So that's why when they build structures, those beams and planks are placed this way rather than this way, because there's an increased resistance to rotation when they're placed this way. So the moment of inertia is defined as a mass times the radius from the axis of rotation squared. Because the moment of inertia is a mass times a distance squared, usually the units that you'll see are kilograms times square meters. You might see other units as well, but you have to understand it's a unit of mass times a unit for distance squared. When you're dealing with regular objects, there are a number of formulas already available that you can look it up. So you could look up the rectangular solid if it was laying flat or if it was laying on edge and compare the moments of inertia for the two objects. But when you're finding the moment of inertia of an area that's an irregular shape, then we need integration. So let's take a look. So if we had an area bounded by the top curve f of x, the bottom curve g of x, from x equals a to x equals b, and if that area had a constant density, so that would be a mass per area. I know typically we talk about density as mass per volume, but here we're going to be dealing with K as mass per area because we're working with an area. We can find the moment of inertia about the y-axis by taking the mass of this representative rectangle and multiplying it by the distance from axis squared. And we're going to sum all of those slivers up by integration. We can summarize that with our integral from a to b. Our mass will be this density times our area. And how do we express area of this rectangle? It will be f of x minus g of x times dx. And I'm going to put the dx here. And I multiply, it's a second moment, so I have to multiply by this distance x squared. When I simplify that, I'm going to take the k outside of the integral sign because it's a constant. I'm going to move the x squared in front times f of x minus g of x dx. So this is the formula for finding moment of inertia about the y-axis of this area. There's another value you'll probably be asked to find, and that's radius of gyration. And the relationship we already mentioned was moment of inertia will equal the mass times that radius squared. So if I'm working with respect to the y-axis, then I'm going to be working with this formula. And I can solve for r sub y by dividing I sub y divided by the mass and then taking the square root. And what that radius of gyration means is that if you were to take a mass of the same value and place it on a line that is this distance away from the y-axis, it will have the same rotational inertia as your whole area does. Let's take a look at an example to see how this works. Our example says find the moment of inertia and the radius of gyration for the region bounded by y equals cube root of x equals 8, and the x-axis with respect to the y-axis. If the region has a constant density of 3 kilometers per square meter, assume all dimensions are in meters. So our first step is to draw the area that we're dealing with. So y equals cube root of x looks like this. X equals 8 is this. And the x-axis. So this is our region. We're asked to find the moment of inertia and radius of gyration with respect to the y-axis. So we're going to use vertical rectangles. So here's our formula for moment of inertia with respect to our y-axis. Even though there's a y there, notice it's all in terms of x. So be careful with that. Our density is 3 kilograms per square meter. So if we take that density and we are taking the integral from 0 to 8 of x squared times f of x, which is cube root of x, which is x to the 1/3, minus 0 dx. So understand that when you take that density and multiply by the area, that's going to give you mass, and we're multiplying by that distance squared. Now we simplify this. So that's going to be x to the 2 plus 1/3 will be 7/3. Now we integrate. So that will be x to the 10/3 divided by 10/3, so 3/10. And that's going to be 9/10. 8 to the 10/3, cube root of 8 is 2, so 2 to the 10th minus 0. I'm going to write that as a decimal. It's 921.6, and this is important. You need your units. Remember, your units are mass times radius squared. Our mass is in kilograms times our radius is in meters, so times radius times meters squared. So that would be the correct unit for that moment of inertia. 921.6 kilograms times meters squared. Next, we need to find the radius of gyration. And in order to do that, I need to find the mass of this area. And I find mass by taking the density times the area. So the density is 3 times the area of this region. So the integral from 0 to 8 of top curve minus bottom curve. So x to the 1/3 minus 0 dx. That integral will be 3/4 x to the 4/3. So 9/4. Cubed root of 8 is 2. 2 to the 4th is 16. 4 will cancel, and that will be 36 kilograms. Because our mass is kilograms per square meters, and our area was in square meters. So our mass is 36 kilograms. Now we can find our radius of gyration. We will plug into this formula, and I'm going to put my units in. So it's going to be 921.6 kilograms times square meters divided by 36 kilograms. The kilograms will cancel, and we get, when we take the square root of 921.6 over 36, we'll get 5.06, and when we take the square root of meters squared, we get meters. So a mass of 36 kilograms on a line 5.06 meters away from the y-axis will have the same rotational inertia as this area does with respect to the y-axis. You can also find the moment of inertia with respect to the x-axis. In that case, we're going to define everything in terms of y. So if we took an area bounded by f of y and g of y between y equals c and y equals d, and we wanted to find the moment of inertia of that area with respect to the x-axis, it would look very similar, except then everything is in terms of y. So the moment of inertia with respect to the y-axis would be equal to our constant times the integral from c to d of y squared times f of y minus g of y dy. So K is the density in mass per area. And if we take that mass per area and multiply by the area, that gives us the mass. And when we take that mass and multiply by y squared, we get the second moment. Let's take a look at an example. So this is the very same example, except now it's with respect to the x-axis, but it's the same region and it has the same density. So we've already calculated the mass to be 36 kilograms. We don't need to do that again. Now we have to calculate the moment of inertia about the x-axis. We're doing everything in terms of y. So we have to write this as a function of y. If y equals x to the 1/3, then x will equal y cubed. So this is our function. And if x is 8, I need the y value at that point is 2. So I'm going from 0 to 2 rather than 0 to 8. Density is 3. The integral from 0 to 2 of y squared times f of y. F of y is x equals 8 minus g of y, which is y cubed, dy. Simplify it, so it's going to be 8y squared minus y to the 5th dy. And we integrate, so that's going to be 8/3 y cubed minus 1/6 y to the 6th. So 2 cubed is 8, 8 times 8 is 64 thirds, minus, one of the 2's will cancel with that, so we'll get 1/3 times 2 to the 5th, which is 32 over 3. 32 over 3 times 3 will just be 32. And that's a moment of inertia, so my unit should be a mass times a square distance. So it's 32 kilograms times square meters. Let's find the radius of gyration. So I plug into my formula. The radius of gyration will be equal to the square root of the moment of inertia, 32 kilograms times square meters. Divide by 36 kilograms. Again, kilograms cancels, and then we'll have the square root of 32 over 36, which is 0.94. And the square root of meters squared is meters. So what that means is if we took a mass of 36 kilograms and placed it 0.94 meters away from the x-axis, so either above or below, it would have the same rotational inertia as this does. The next video is going to be on moments of inertia of volumes. So when you're ready, I'll see you.